Good afternoon, all. So now we are moving on to session 2 of International Conference on Advances in Nanomaterials for a Sustainable Future 2025, and we are having Dr. Raghu Chatanakodi from Department of Physics, National Institute of Technology, Calicut. And now I welcome Dr. Julian Joseph, Assistant Professor, Department of Physics, St. Joseph's College for Women, Alappuzha, to extend the welcome.
Good afternoon, one and all. Now we have Dr. Raghu Chatanakodi to give an expert talk on the topic Computational Atomistic Modeling for the Design of Energy Materials. Dr. Raghu Chatanakodi is a distinguished academic and researcher serving as a professor in the Department of Physics at the National Institute of Technology, Calicut. He completed his BSc in 1993 from Regional College of Education, Mysore, and later pursued an MSc Physics from the University of Hyderabad in 1995. Dr. Chatanakodi earned his PhD from the prestigious Indian Institute of Science, Bangalore in 2002. Following his doctoral studies, he gained valuable international research experience during a 2-year stint in Arizona State University, USA. On his return to India, he contributed to industrial research at the General Electric Research Center in Bangalore for 2 years. In 2006, he joined NIT Calicut, where he has been an integral part of the institution for the past 18 years. Dr. Chatanakodi resides in Karandur, Calicut, and continues to inspire students and contribute to the advancement of physics through his research and teaching. And I know him as a member of my doctoral committee during my PhD at NIT Calicut, and I remember the way he supported my research and documentation process during my research career. And as a continuation of the previous session, sir is going to deliver a talk on how to model and design energy materials. He would definitely motivate us with this enriching session. And on behalf of ICANSF, PG Department of Physics and PG Department of Home Science, I extend a hearty welcome.
So, good afternoon, all, and I, at the outset, thank the organizers of this international conference on advances in nanomaterials for sustainable future for inviting me here, especially Julian. As she says, I know her for quite some time. Even before her PhD, when she was a assistant professor on contract in IIT Calicut. And so she first came to Calicut, and now, so she finished her PhD and she's here. That's what we hope all our students will teach and take up research. It's always not possible, but that's the hope with which all of us sit in a master's program and a PhD program. Thank you again. This is my first visit to this place. I passed through this place. So it's a very nice campus. I hope all of you enjoy studying here. As the theme of this conference is sustainable future, this is something which is really a serious occupation or focus of human thought, because the century previous to us, from let's say 1920s to the end of that century, and 20 years of this century has seen enormous development using resources we thought are freely available, and we didn't know what we are doing when we are spending those resources so freely. But over the last 25 years, we have been able to put into practice at least some checks and balances, or at least have thoughts on how we are polluting the world, changing our environment, and how we are finishing very valuable resources without even thinking of where they come from or what is the damage that's being done. So, in that sense, this is a very important key area to really have a conference on. And this is an area which will be very easily funded when you go for a research project or a conference proposal or anything. So, it's really energy and sustainability related topics. They cover a wide range of subjects, by the way: physics, chemistry, biology. Sustainable practices go deep into economics and commerce also, because it's not just science that plays a role in that. There's a lot of role for social sciences also. Anyway, so my topic today is about modeling of materials, particularly for energy applications, and we do something called as atomistic modeling. Atomistic modeling, will come to it. It is to assemble a material by atoms, and the smallest kind of most useful materials that we deal with are nanomaterials, and these are assembled through atoms. There are various ways of developing. There's a bottoms up approach, there's a tops down approach. All these lead to tiny collections of atoms or molecules which are acting in concert and producing very important material. And we do this computationally. We don't have to go to a lab to do this. And our insights by doing it on a computer are very useful. I hope at the end of this talk that will be clear that such insights are very useful to uh, arrive at the proper material that you want to use for your energy application, and not go around in a combinatorial way. You try all combinations of all kinds of material and waste a lot of chemical in the process. Many of them will turn out to be not very useful to you. That's the approach. Um, I'll first talk about the need for modeling, and the kind of modeling that is being focused today is something called as based on density functional theory, which is known as a first principles method. And then I'll focus on some of the applications that we are doing in my research group. We are right now looking into something called as the electrochemical oxygen reduction reaction, which is a fundamental reaction in a fuel cell. Uh, then we look at, so these electrochemical reactions need a catalyst, and we look at how metal oxide catalysts can be effective replacements for other catalysts which are normally used, which are precious metal catalysts. Then there's also another important energy-related reaction, which is known as a hydrogen evolution reaction, which produces hydrogen as a fuel. And we look at some catalyst materials for that. But the idea is to give you a feeling that computer simulation of materials gives useful insights into producing good material. Okay, so there are a lot of materials which lie at the interface of physics, chemistry, and biology, and you can form very useful, interesting systems. So nowadays, I don't know, those pointers working and it won't reflect on the board. That's the problem. Okay, so on the left side, you see there are devices called as spintronic devices. Nowadays, you hear about computing using quantum mechanics. So there's something called quantum computing. Normal computing is done by storing charge or not storing charge. So there are two states, zeros and ones. So we talk in terms of zeros and ones, binary, right? Now you also know that there is something called spin, and spins can point either up along an axis or down along an axis, and that pointing can be read as a 0 and a 1. So something which is usually stored in form of charge is going to be stored in form of spin, and that leads to spintronics, or that's a counterpart of electronics which works on charge, but this is something which works on spins. And I can manipulate spins by using magnets. Like, for example, I can change the spin during the orientation there, during the process of transmission, when I change the nature of the magnetic field. Or I can have, nowadays, quantum sensing and metrology measurements have become very important. You see, India has set up the National Quantum Mission. A huge amount of funding which government of India wants to put into quantum computing. And in the last year's budget, our finance minister has announced nearly 6,000 crores outlay over the next 8 or 10 years for developing quantum computers. Because we missed the first computing revolution, which was in 50s and 60s, which was completely taken over by Americans. Now we have a great competition. We are a little behind. We are left behind by the West as well as China. So we need to catch up, and Government of India set up NQM, the National Quantum Mission, where sensing and metrology based on quantum mechanics is one of the key areas. Then there is also molecular electronics, where electronic comes down to the level of molecules. Because I would like to have a more complicated functions in my electronic chip, and I need to make the elements. I need to pack in more and more transistors, and therefore I would like to come down to atomic or molecular levels. So the picture there shows a molecule sandwiched between two gold electrodes, and it can conduct. So this called as this is a simple example of a molecular wire, a wire which conducts, which is at a molecular level. The concept has come back in 70s when Mark Ratner proposed that. We have a lot of work on organic solar cells in our department. I myself do calculations for our head of the department, Dr. Shivaji Reddy. That is also a sustainable energy initiative. Right? Then there are energy materials, electrocatalysis, which promises supply of clean energy. So we have various catalysts catalyzing various processes. Like for example, production of peroxide, hydrogen peroxide, or ammonia, all these kind of catalysts. Right. Uh, the focus is on sustainable and green energy. We have an intense decade of non-renewable energy resources. You must have been seeing this kind of data for quite some time now, over the last two days. Uh, Oil, coal, natural gas, nuclear energy, all these are not sustainable and contribute to global warming. If you look at data, um, the American, so if you look at annual CO2 emissions, I hope this is the latest data, this is given by my student. The emissions due to West, typically represented by America, is tapering off the second lower, higher curve, but China is rapidly picking up, and India is also somewhere there. We are contributing quite a bit to global emissions. And in about 20 years, we will be one of the largest consumers of energy, mainly coming through our population. See, all of us have cars. Have you seen how crowded it is on roads nowadays? Ever since COVID, it is very difficult to walk on roads or just pass on roads. And the amount of fuel that we are using is extremely large. So we need to develop other sources of energy, and one of the possibilities is electrochemical sources. There's some prototypical picture. So electrochemical sources on the left, you can see that they contribute to a lot of processes. There I can have sustainable manufacturing without using too much. One example here I want to cite is the production of ammonia, which is a fundamental chemical for the fertilizer industry. A lot of other products which come out of industry. So if you want to make ammonia, you might have all learned in your BSc or even school that there is an important process called as the Haber process. Right? The Haber process requires you to maintain a very high temperature over the iron catalyst. Are there? So where is that temperature coming from? It's from burning of coal, because that's where the source of electricity and all other heat comes from, primarily in our country. Our country requires a huge number of production of output of fertilizers, because we are predominantly agricultural in rural India. So, are there sustainable ways of doing that? It's possible to produce ammonia in an electrochemical way, but it requires a smart catalyst. So, what is that catalyst? So that's a kind of, so the smart production of chemicals and energy are both a requirement for a sustainable future. Hydrogen energy, we are talking a lot about that. Europe and America are going into trains which are powered by hydrogen. There's a very recent report on utilizing hydrogen resources inside our Earth. I saw this report now twice, that a huge deposit of hydrogen is inside the Earth. We don't know how to tap it. If we tap it, a very small, tiny fraction of it is enough to completely eliminate the use of fossil fuels. But how will you manage hydrogen? How will you transport it? All these are issues, right? So we need to design electrochemical catalyst, fuels, solar photovoltaic materials, all these kind of things. And we need to research about better storage materials, like for example supercapacitors. In doing all this, we need to synthesize materials, characterize them, test materials which lead to efficient energy production. So these are our mandates. So uh, uh, So particularly the last one, finally we have to have a material and a device which is efficient in energy, efficiently produces energy. So we need to do all these things. Now why computational methods? This talk is about computational methods. Computer-based modeling allows for a fundamental understanding of how a material behaves, how to build materials and what are the interactions which determine its property. Because finally a material is made of atoms and those atoms interact. And that is the way the property of the material is decided. Whereas, for example, whether a material is a metal or a semiconductor or an insulator. These are all decided by how the atoms of this system overlap, bond with each other, how electrons are arranged in this atoms, right? Uh, Keep on doing experiments without any guidelines, then you might end up uh, uh, wasting a lot of money and material. Experimentation may turn out to be expensive on the large scale. We want materials and devices in very large scale deployments. Okay, so we need to first design materials with tailored properties, and it points out to understanding and being able to evaluate and design materials for various applications specifically. And their computational methods are useful. On the other side, uh, theory as an analytical theory, pen, paper, pencil kind of theory. Uh, if you look at quantum physics, very few problems can be exactly solved. We know how to solve the hydrogen atom by at least by MSc time. We know how to solve the hydrogen atom. Then there is something called as a molecular ion, H2 plus, which is exactly solved. You can write what is the solution for that problem. Harmonic oscillator, all of us will study. Other than this, there are very few problems which you can really solve, and that gives you a possibility that you can solve them using computers. And what theory actually does is to give you results in important limits. It's a very weak interaction or non-interacting system. For example, we fill up the atomic energy levels and get the periodic table, right? What is that principle called? It's called as the Hofbauer principle, right? And that is by understanding that I put one electron into an energy level and then I put the second electron in a different spin, but we think that these electrons don't interact. So we are therefore in analytical theory working in regimes of big approximations which do not represent real systems. In such situations, numerical solution and computer simulation for complex materials becomes very important. So the kind of complex materials we are looking at are surfaces, junctions, interfaces between materials, large molecules, etc. So that is the reason for computational procedure. And does it really work? Can you really design a material using computers? The picture you see is of a material, a two-dimensional nanomaterial called as phosphorine. It's like graphene. Many of you will be knowing what's graphene. It's a one atomic thickness layer of carbon, right? Now, if I try to do the same thing for phosphorine, it will not remain flat. It will be puckered. You see, there's ups and downs. This picture was made on a computer in my lab. One of my students studied phosphorine. In fact, she looked at how phosphorine can be used to store hydrogen. I don't want to carry hydrogen around in cylinders. That's too dangerous. If hydrogen is attached to these kind of materials and I can release it whenever I want by just shaking it or just heating it slightly, then I'll have hydrogen. Suppose I want to run that kind of hydrogen in my car. I don't want to carry a hydrogen cylinder around because that's too dangerous. Already so many cars are going on fire, right? So I just want to get this hydrogen released at the proper time. So it should be absorbed on a material. Now this material, phosphorus has several allotropes. There is black phosphorus, all kinds of phosphorus are there. If I try to make it one-dimensional, two-dimensional, then there is phosphorine. It becomes phosphorine, and this is the black phosphorine allotrope is the most well known. This was developed as a computer uh, simulated material. That's the paper there. It came in physical review letters, and later in about 2 years' time, it was synthesized. That's the lower one, nanoletters paper. It actually broke of single layer blue phosphorine, a new phase of two-dimensional phosphorine. The other one is a theory paper, semiconducting layered blue phosphorine, a computational study. So this happens. Either a material is synthesized, which we don't know much about how its atomic constitution is, and we study it computationally to understand it better, or we computationally design a material which is later synthesized. So this is always happening in science, and we are all hoping that this keeps on happening. That's why we work. Yeah, I can predict a lot of different materials. I just skip this part. What is atomistic modeling is basically to build a material from its constituent atoms. Atomic hypothesis is known very long back. See, right back in 60 BC, this Greek thinker, Paris, says that it is of great importance how atoms are put together. Of particular relevance are arrangements, distances, bonding, collisions, and motion. Everything that we know about matter was known then, right? This is the book called On the Nature of Things. You will see its versions or translations on the internet. Okay, so you have to build a material from constituent atoms. These are governed by the laws of quantum mechanics, and these atoms, it need not be just atoms, it can be molecules, etc. Molecules or materials which we use in our daily life are collections of interacting many atoms. And these atoms are in turn made of electrons and nuclei. What we require in atomistic modeling is to only know what is the crystal structure if you have a crystalline material. So I just want to know what is the unit cell. It essentially tells you where are the atoms located or what are the atoms which make. And I want to know which atom is making. For example, if I take a zinc oxide crystal, I want to know where the zincs are sitting and where the oxygen is sitting. And I want to know it is zinc and oxygen. That is known by knowing what is the atomic number, right? So if you can model your material knowing these two things, what's the crystal structure, or where are the atoms, what are the atoms, then we say that this is a first principles modeling. Nothing else is required to really make up it. All other properties, what's the crystal structure, how does it cleave out into a layer, what's the mechanical strength, what's the elasticity, or is it brittle, is it a conductor, is it a semiconductor? All these come from just doing this atomistic modeling. And that's the kind of vision we have for computational atomistic modeling. Okay, so typically a molecule or a solid is a collection of large number of electrons and nuclei, and they are all interacting through Coulomb forces. And in physics, we write what is a energy expression, the Hamiltonian. It consists of kinetic. So electrons are moving around. So electrons are moving around. There is a kinetic energy of electrons, a kinetic energy of ions. All these terms are there. So this is an extremely complicated model. It's hard to really solve it. What we have to do with this model is to solve the Schrodinger equation. You are must be familiar with Schrodinger equation, and you must be familiar with the fact that it's practically impossible to solve this, especially in the case of very large number of uh, electrons and nuclei involved. That's because the large number of degrees of freedom that's present. Okay, so approximation should be made. If I solve it for the atom, I'll get that left side picture of orbitals. If I solve it for a solid, I'll get what is known as a band structure. This is called as the electronic structure. And that's the end product of our calculations. That you get a band structure. The horizontal axis is a k-axis, wave vector axis, and the y-axis is energy, and it tells you the allowed energy levels in the solid. Okay, and just like I fill electrons into atomic levels, I just fill electrons into this solid's energy levels, and I'll get a solid. And the properties will depend on it. Okay, the procedure we use to solve this is a method called as density functional theory, where the electron density is the fundamental variable and not the wave function as usual. Okay, so we don't go into the details of all these calculations. It just rests on this fundamental principle that if you take the lowest energy level, the ground state energy is a unique function of the electron density. And the many electron problem represented by that equation can be in this approximation, this density function theory, be reduced to a single electron problem. So it's like a single particle moving in an equivalent potential. I'm just giving all those details. This methodology is extremely well known. Got the Nobel Prize in 1998 for chemistry, because chemists use a lot of density functional theory, much more than physicists do. It is given to Walter Kohn and John Popoul. John Popoul is a quantum chemist. Walter Kohn is a physicist. Though density functional theory developed through the work of Walter Kohn mainly, equally shared between Kohn and Popoul. I don't know if there are chemists in this audience. You might have heard of packages like Gaussian. It's a very popular package to calculate molecular structure. Mainly rests on the work by John Popoul. Challenges are that these are very complex calculations. So researchers have to determine its convergence, what is the potential. You all know that to solve the Schrodinger equation, I need a basis. So there are several different kinds of bases which are used. You should decide all that. Codes are available. They are professionally packaged codes. They are very, very large codes, which you might spend tens of or 15 years to write one package. So they are already available, and you don't have to invent that wheel again. And they are computationally intense. I cannot do it on a simple desktop like that. I need very large, at least multi-core processors or high-performance computing. See, multi-core processor is not a surprise now. Most of your phones are multi-core processors, right? At least 8-core phones will be there nowadays, minimum. Otherwise, you may not be able to see Instagram that very well, right? So it's that same ease. My calculations have to run faster. I want a large number of cores. So these are the available codes. I'll just introduce some of them. I use something called VAST, V-A-S-T. That's called as the Vienna Ab initio simulation program. If you look down here, there are free codes which are free for academics to use. Some of them have license fee, like VAST has a license fee. It's a perpetual license fee I can use throughout lifetime. About one such is about recently I'm going to review. It comes to with taxes, it comes to about 2.4 lakhs. So these are the way. So siesta is a Spanish code. Siesta is to sleep, right? Also, people in Spain love to have a nap in the afternoon. And that is called as siesta. And this stands for Spanish Initiative in Electronic Structure, something like that, siesta. Abinit is a German code. Gaussian 16 is very popular with chemists. Most spectroscopists will use it because you want to know where you see a spectrum. I want to identify the energy levels properly. I need a Gaussian calculation. So these are some of the codes. Yeah, it can give a lot of properties. What all can it give? I can do dynamics. I can do molecular dynamics. It's how the atoms which constitute my solid or molecule move around. If I increase the temperature, how do they wriggle around? That kind of activities I can get from solving this. I can get optical properties. Not very good, but I want to know what's the band gap. I want to know what's the optical conductivity. These kind of things. Magnetism. What's the magnetic ground state? Is it antiferromagnetic? Very dangerous to do with these codes. You'll never predict it properly. Is it ferromagnetic? Or is there a local moment? Is it a metallic magnet? A lot of different kinds of properties can be calculated. You need some kind of infrastructure. This is the kind of facility we have in NIT Calicut. This is called as the Madhava cluster, named after the legendary Kerala mathematician Madhava. It has 1,200 cores altogether. In one box, it will have 40 cores. So it has a processor of 20 cores and another processor of 20 cores. And you just need to submit jobs to this. It doesn't have a monitor or anything. You just submit job, and after some time, it will give you the answer. That after some time, it can be a day, a week. 2 days back, my students are complaining. Some jobs are still lying around here. They have been running for 6 months. So I happen to be the administrator of this facility right now. So. Yeah, it's not charged right now. Students don't have to pay for. Otherwise, abroad, when you use this kind of facility, there is a concept called CPU time. How much computing time I use, and that is charged per hour of CPU time. I have to pay something. And so when you write a proposal, you can actually add it, add that fund into your proposal. Okay, but don't be disappointed. You can do it on a modest workstation also. There are people, especially, there are these schemes like SCRP, TAR, and all that. Teachers come to us and we mentor them for a project. I have one such person in for a college. He is working on this kind of TAR project, and he has purchased a modest workstation for some 2 lakhs and some kind of. When you have that kind of funding, you can always get that. There are free codes, quantum espresso and Abinit are free. You can set up these calculations on your own. They're easier than doing experiments. So people accuse us of not doing any fun. We just sit in our chair but it's not so simple as that. Interpreting, understanding, and interpreting. For example, if I do a calculation for silicon, this code will immediately predict silicon in the lowest level of approximation to be a metal. And that's because of the kind of very drastic approximations which are done in the code. So silicon, which has a band gap of about 1.1 eV, the band gap will come to about 0.3 or 0.45 eV, nearly a metal. And then we have to see how to improve that, right? So if you are not careful, you will end up with a lot of mistakes. Okay, we can deal with surfaces and molecules. I need to construct a box around that, a simulation box, and put it in that. And that box identifies the periodicity. For example, this surface is periodic in X and Y direction, but has a vacuum gap to the top, which actually gives its two-dimensional nature. Molecule is one-dimensional. There's a chain molecule. I can put it in a box, and it is one-dimensional chain along the z-axis, continuous, but there is a gap, vacuum or nothing around it in the x and y direction, right? I can build clusters. This is a cluster we have recently built and studied. It's a 5 copper cluster. It's a nano cluster of copper, Cu5. This is a two-dimensional nanosheet of a very well-known 2D material, tungsten sulfide. Its top view looks like that, but actually it's continuous in the x and y direction, but on the z direction there is a gap. See, that's how I built my simulation box. Okay, now let's come to how I can apply this to electrochemical catalysts. One of the fundamental processes in an electrochemical cell, in a fuel cell, is what is called as an oxygen reduction reaction. What it does is it basically oxygen mixes with hydrogen and produces water, and we have two electrodes. At the anode, hydrogen is oxidized, and at the cathode, oxygen is reduced. And I don't know why this is not working. There's a demo there. The things seem to be running. Is this? It's not in the slideshow mode. Will it not go to slideshow mode? Yeah. It still is not working. Anyway, so let's try to do without that. Fuel cells basically convert the chemical energy into electrical energy. So what happens here? I'll just point it out here. That's an animation. Yeah, fine. So what happens is that hydrogen left side and is attracted to the air and gets stripped of its electrons. The electrons flow in the outer circuit, and the hydrogen ion then migrates across through the porous membrane onto the cathode. And at the cathode, it mixes with oxygen, which oxygen is being pumped into the cell and it produces water. And that reaction requires the electron coming from the outer circuit to come in and completes the circuit that way. So if I can use this cell to produce energy, electrical energy, by utilizing that flow of electrons, right? And this is a green device in the sense that the only thing that comes out of this is heat and water vapor. See, these kind of devices were used in some of those Apollo missions and all that first time. And space is a sector which really requires that, but you can use it in transportation. Now, only problem is that the catalyst which is used in this is very expensive. Okay, if I want to deploy these devices large scale, then I need to spend a lot on this catalyst. So we'll come to that. The oxygen reduction reaction converts oxygen to water at the cathode, and it has two possible pathways. There's a 4-electron pathway and a 2-electron pathway. The 4-electron leads to complete reduction to water, whereas the 2-electron pathway leads to formation of hydrogen peroxide. That is an important industrial chemical, but to the efficiency of the fuel cell, I would prefer a 4-electron pathway. So how will you design materials which normally work in the 4-electron pathway? The 4-electron pathway means there are 4 steps. Oxygen gets adsorbed, then it splits up, and there are further intermediate steps where there is a hydroxide species and then OOH species which get finally converted to water. So there are 4 steps. Each step has 1 electron participating, and so it's a 4-electron process. The 4-electron pathway is preferred because the fuel cell is more efficient. Okay. So this reaction proceeds by the or initiates with the oxygen adsorption, and the breaking of the oxygen-oxygen bond is very difficult because it's a stable double bond. And the cathode reaction, the ORR, is much slower than the oxidation of hydrogen at the anode, and therefore it needs a catalyst. And this is the biggest problem, that ORR, the oxygen reduction reaction, is sluggish, and it's a key bottleneck in this process. So I want to improve that. The other thing is that the catalyst which is standardly used in this is platinum. And platinum or platinum-based catalysts are very scarce, difficult to get. They have high cost, and they have something called as poor carbon monoxide tolerance. In some kind of cells, there is something happens which is called as carbon monoxide poisoning of the platinum catalyst. So these kind of things are disadvantageous to the functioning of the cell. Okay. So we need to find out materials which can replace platinum, especially economy and abundance. These are two things. Reduction of cost and abundant material should become a gap. So the major focus is to reduce the use of platinum, palladium, molybdenum, these kind of precious metals, or gold, silver. That's cheaper, but still is a precious metal. So reduce the use of precious metals and complete. So look at if you can replace this metal completely with something like a metal oxide, which is much cheaper. Okay, simple transition metal oxides or mixed metal oxides, transition metal dichalcogenides, MXenes, which are a new set of systems. Are these suitable materials for your catalyst? Okay. DFT can help in this by looking at whether the structure is stable, the material that you're looking at. It can calculate what is called as surface adsorption. Now, oxygen should first get adsorbed to your surface, and surface adsorption is something which is very easily studied with density functional theory. It can calculate the free energy of reactions, and that decides which is your rate determining step and all. Or it tells you the efficiency of your cell. It can also find out what is the reaction barrier in this process. So all these kind of information you can get from modeling. Okay. For example, I can calculate what is the binding energy or adsorption energy. Especially studying of surfaces, this adsorption energy is very important. If I look at that slab of, this can be a slab of gold, I can put a molecule in that in the simulation cell, and I can calculate what is the binding energy of this molecule to this slab. The binding energy is given by the, I first calculate the energy of total energy of system without the slab of only the molecule, so I get that E mod. Then I calculate the energy of the system without the molecule, only of the slab. Then I calculate it with both the slab and the molecule put on the slab. So this difference, slab plus molecule minus the total energy of the slab alone and the molecule, this will be the binding energy, right? It will tell you how strongly this molecule is adsorbed onto this one. So we have various regimes of adsorption. We have chemical adsorption where a bond is formed, or there can be just weak van der Waals forces which are binding, which is called physisorption. So if I spill some water on this table, there is some kind of physisorption which is binding, and that energy is of the range of 0.5 eV or something. Chemical adsorption binding energies will be 1 electron volt and if I look at 2 or 3 electron volts energy, that is very strongly absorbed. It can even distort the surface or change the structure of the surface itself. Sometimes the molecule breaks up. So we want to see if oxygen binds to the surface, will it break up or not? Or will it remain as oxygen? If it remains as oxygen, it's very weakly bound. For example, the oxygen bond length typically in gas phase is about 1.2 angstroms. Now, if that bond is stressed, then I would say that's an activated oxygen. So I get this to absorb, solve Schrodinger's equation and see if it's absorbed, and say whether my oxygen is still remaining almost like gas oxygen or like an activated oxygen, which has a strong, longer bond. Okay, so the material we have studied predominantly is titanium dioxide, which is a very well-known catalyst material. It's highly used as a photocatalyst. Why we have looked at titanium dioxide is primarily because it's abundant. It's non-toxic, and that's very important. When you're environmentally, you need non-toxic materials, and it's highly stable under various conditions: acidic, basic, all these. And I have looked at the particular phase of TiO2, which is called as anodized TiO2. I look at a 101 plane of its surface. Okay. Can TiO2 be a good oxygen reduction catalyst? Answer is no, because even the initial step, if I calculate the binding energy of oxygen onto titanium, that binding energy is too small. The oxygen bond length is not stretched at all. It will be just some 1.28 or something. Slight stretching, so it fizzes out, and that's why the material titanium dioxide is not a well-known electrochemical catalyst. It's used as a photocatalyst, but not as an electrochemical catalyst. And the question is, how can you make it into an active electrochemical catalyst? I can do that by introducing some surface defects or vacancies or things like that. Or I can do doping. These are all aspects which we have studied. We have looked at doping this material with niobium, and we see that the oxygen binding and the oxygen reduction reaction parameters improve a lot that way. Okay, so what I'm going to point out to you is that I can look at defects on the surface. So a real material will have defects, right? For example, surface can have steps. You can see that there is a sudden step, and then there is a flat area, and then a step. So actual surfaces are like this because that's the way materials grow. So these are called stepped surfaces. At the step edge, so there's an edge for every step, and at the step edge there will be atoms which have much lower coordination. Inside the bulk of the material, you'll have the highest coordination for an atom, maybe 6 or 5. In TiO2, we see there are titanium atoms which have 5 coordination and 6 coordination also. On the edge, step edge, I have a 4 coordinated titanium. Now that 4 coordinated titanium has some unsatisfied valencies. So that will become important in improving its reactivity. Okay, so let's leave some of these details. The other way I can think about improving the reactivity of the titanium dioxide surface is to introduce defects. So I can create oxygen vacancies. Oxygen vacancies are very easily created on a oxide surface. The classic example is that of zinc oxide. Zinc oxide has a lot of vacancies on the surface. So I can remove various oxygen atoms. Now on a computer, these are very easy to do. I make this model and just plug out the oxygen. My experimentalist colleagues say that they in fact talk very insultingly that for you it's very easy to sit in the chair and create that defect. But it is possible. So there are various kinds of defects. I just listed them out. I can, so there are oxygens which have 3 coordination, 2 coordination. I can create various defects and look at oxygen adsorption, and I find that the oxygen, moment the defect is there, if I look at the adsorption of that defect, then the oxygen becomes activated and the OO bond is stretched. Now what is the length? It becomes 1.3 to 1.3. So if the oxygen bond length is in the range of 1.32 to 36, then in materials theory this is called as a superoxide. if it is much further stretched, if it is 1.42 to 1.48, it's peroxide. In the peroxide regime, it's very easy to break off one of the oxygens. The bond is really weak, and that happens when this atom, one of the oxygens gets strongly attached to the surface, and a lot of electron density transfers from the oxygen-oxygen bond to the oxygen-metal bond. So this kind of thing is happening, and our calculations show that the adsorption of oxygen is larger on the effective surface than on the perfect surface. So the oxygen is activated on both the step surface as well as the defective the vacancy surface. Okay. Not only that, the vacancy surface can hold more oxygen. Instead of just binding one oxygen, it can hold 2 or even 3. So that kind of, then if I'm holding that many oxygens, I get much more activated oxygen to participate in the cell reaction. So the other thing that we have tried to do is to decorate the PiO2 surface with tiny nanoclusters of gold. And when we do this, we see that the oxygen activity improves. So let me just drop all these details because I think I'm almost the schedule time is over, but maybe we can take about 10 minutes more. Right. So when we put gold clusters on this, then you see that oxygen binding on the titanium atoms near the gold cluster, they suddenly become much stronger. And that's because of the transfer of electrons from the gold to the titanium. And once the substrate becomes electron rich, it can easily bind oxygen. Right? So, gold is very well known in catalysis, but we want to use gold to the minimum because we want to keep the cost of the entire process to be minimized. So we say that we want to see a very good catalytic activity in minimal gold loading. So we have been able to do this, and we see that if I have a gold cluster, there is improved oxygen adsorption on. So we looked at a 3 cluster of gold, a 5 cluster, and 7 cluster. On all these Au3, Au5, Au7, all these we find an improved oxygen adsorption. We also find that the oxygen bond length depends on how you rotate the cluster. So if you see the cluster, if you just rotate this. If you rotate this cluster around the axis, then at certain points the stretching of the oxygens increases. So these are things which we can see on the computer. I can't just go and point it out there because then I have to leave this mic, and that's a problem. Okay, so we in the earlier situation when there was almost no adsorption on bare titanium dioxide, on the Au decorated titanium dioxide, we see a very strong adsorption of nearly 2.39 electron volts, and that's a function of how the cluster stayed. So, what my student found out is that you can. So this tilting or rotation of this cluster is possible on a natural surface when I have a step, because at the step there is always, when a molecule adsorbs, there is a tilting. So the step surface will naturally lead to tilting, and that is where we find the best adsorption of. So we did this study, and yeah, that got published in Nanoscale Advances recently. This is the thesis work of my student Mohammad Fasil. He is, yeah, his defense is almost arranged. He's writing the replies to his examiners. So hopefully he'll graduate soon. Then we try to do the same thing for copper, because copper is cheaper than gold. But then we find that copper reacts very strongly to oxygen. And what happens is that the copper reacts so strongly that the cluster copper is distorted and it breaks up and forms copper oxide. So then the question became, well, if in a catalyst you have to retain the catalyst for the next reaction the next adsorption zone. So how will you protect this catalyst? So one of the ideas that came to us is to make it absorb something else so that its activity for oxygen is slightly reduced. So can you tune the activity? We found that if you cap the cluster with organic molecules, like in this case I have a benzene molecule attached to the cluster, then the oxygen still remains activated, but the cluster doesn't get distorted or break up. See, again, I'm talking about the oxygen getting absorbed on the titanium dioxide. That on the titanium atoms. So I'm actually talking about at the interface between the copper cluster. It's not absorbing on the copper, but at the interface between the copper and the titanium. So the titanium atoms at the proximity of the cluster, they are the ones which become activated. So we call this as ligand-assisted stabilization of the copper cluster on the PiO2 surface. Actually, if you do molecular dynamics simulation, you see that certain copper-copper bonds stretch up, like the ones which are marked in blue, they stretch up and lead to the breakup of this cluster. Way to stabilize it is to put organic molecules. We have tried the two organic molecules. Tried means on the computer. So we looked at pyridine and diaphene and benzene. Pyridine and diaphene because they are common caffeine molecules that are. We see that the adsorbed oxygen bond lengths remain the same, and the cluster retains its catalytic integrity. It's most important to protect the cluster. This is like protecting again. See, copper gets oxidized very easily, right? You can see the cloud which you. So you have to protect it with anti-corrosion. This is like an anti-corrosion protection. You cap it such that its activity still remains same. So this is the kind of thing that we did, and still under review. It's still not published. We also, so essentially, you can study any kind of catalytic process, any kind of. In fact, it need not be in electrochemistry alone. You can look at all kinds of catalytic process. You can look at oxygen reduction, oxygen evolution reaction. You can look at HCl, hydrogen evolution. Then there's something called carbon dioxide reduction, CO2-RR. Now, this reaction is very important because we are looking at reducing carbon dioxide emissions. We want to collect that carbon dioxide, making the useful products like methanol, for example. Methanol and other useful chemicals. So, what are the catalysts for that? And nitrogen reduction, I already mentioned it. So, all these kind of reactions can be modeled on a computer using first principles method of solving Schrodinger's equation. One of the important information which comes out in these studies is what is the active site? See, what is the actual site on a surface onto which this molecule binds? Is it on top of an atom? Does it go to the top of the titanium atom? Or is it in between? So there are various sites, like for example, there's bridge, there is valley, all these kind of sites. Will it go and sit there? This kind of information is very hard for experimentalists to actually decipher. So, right. So you can get site information, you can get free energies, you can find out what's the rate determining step by looking at the free energies. You can find reaction pathways. You can plot energy diagrams like this. You can look at chemical thermodynamics, pathway and kinetics. So if I know the pathway, I should know what's the transition state. Oxygen is going to water, there's an intermediate step, or oxygen is becoming OH as a sub-step. What is the intermediate state? And if I know the intermediate state, I can find out what's the energy barrier and what's the enthalpy of the reaction. So many things like that. So all these can be obtained from a kind of calculations. This is another example of hydrogen evaporation reaction. I'll just skip through this. Again, platinum is the catalyst. I want to replace platinum. Here, hydrogen in atomic form gets adsorbed to the surface and then goes away as hydrogen gas. Okay, so actually in the cell there will be hydrogen ion which gets adsorbed and it takes an electron from the surface and becomes and then it either takes another hydrogen from the surroundings and becomes hydrogen gas, or two adsorbed hydrogen in the rightmost figure, two adsorbed hydrogens can form a hydrogen molecule. So that's hydrogen evolution. And again, is the key material. We looked at two-dimensional materials. One of the important catalysts is rhenium disulfide. See, if you look at rhenium disulfide, there are several very well-known HER catalysts. One of the most studied material is molybdenum disulfide, MOS2 or MOSC2. All these are highly studied. But rhenium disulfide it has a layer structure. Most of these metal dichalcogenides have a layered structure in which the metal layer is in the center. If you can see that blue thing in the center, the lower figure, that is in the center, and I have two layers of sulfur or chalcogen on top, and that makes this catalytically inactive. So how do I make this active? I have to expose the metal for molecules to come and absorb, and the easiest way is to cut it, and I can produce things which are known as nanoribbons. I cut the edges, and at the edge the metal will be exposed. And that will be, in fact, there is a very early paper which says that the catalytic activity of observed catalytic activity of molybdenum disulfide is due to the edge atoms. Because in my computer I have a perfect two-dimensional infinite solid, but in my lab sample I have finite flakes. At the edges there will always be edges in those, right? So the way I can computationally create that edge by cutting that, and these are called nanoribbons. In fact, you can make nanoribbons in the lab, and we have studied that. And I'll just skip all this. We have calculated the free energy and shown that the nanoribbons of rhenium disulfide is highly active. The second thing we did was, if you look at a material like tungsten disulfide, WS2. Again, it's a layered structure. You can see that the blues are the tungsten atoms, and there's a layer of sulfur on the top, a layer of sulfur in the bottom. Completely symmetric. Now, I can replace an entire layer of sulfurs with some other metal. So one phase has one chalcogenide layer, the other phase has another chalcogenide layer, or some other non-metal essence. If you do this, this is a two-phased material, and it's called as a Janus material. Janus is two-phased. All your coins are Janus because your one side is your line and the other side is the value of the coin, right? So they're unidentical phases, non-identical phases, and when you do this, you'll upset the electrostatics in this one. This develops an interior polarization because now I have a difference in electronegativity of the top layer and the bottom layer, right? So these materials have come very recently, 2018. People have made it, not just on the computer. They have actually made it in lab. Very few groups have done this. It requires some very intricate deposition techniques, but it's possible to make this, and we have looked at whether these can be good electrochemical catalysts. They are stable. How do I see stability? I look at lattice vibration and what's called as a phonon dispersion. If this doesn't have any negative frequencies or complex frequencies, then I say the structure is stable. And we have again looked at its activity, and we see a decent activity for this. This is a promising material. We are still in the process of studying this. Okay, I'll just summarize now. Atomistic modeling based on density functional theory can provide useful insights into properties of materials. Density functional theory is not the only atomistic modeling, but that is the standard quantum mechanical atomistic modeling. There are classical methods to study. There's something called classical molecular dynamics, where you think of molecules and atoms, and they are all moving under the influence of some classical potential, some Newton's law kind of potential, and they follow Newton's law. Here we actually solve Schrodinger equation. Often these methods will work in tandem with experiments and theory to provide a complete picture. I got into the work on rhenium disulfide because one of my colleagues asked me, there was a paper which was under review, and the reviewers asked, the disturbance. Yeah, so reviewers will ask most unkind questions when you just want to get the paper published somehow. I'm sure all of you who have done your PhD must be having that experience. So the reviewer, how do you know where this oxygen adsorbs on the rhenium disulfide? So we did a calculation for Professor Sandhya and his group, and that's how we got into this. And we even now do that, though these calculations are very expensive. What is the active site? When you do this, your research is, editors look at your research to be more complete. So that way, I say that computational modeling works with experiments and theory together to give a complete picture. DFT calculations provide us with important information regarding active sites, free energy changes, pathways of oxygen reduction, and hydrogen emission reactions. And you can design more efficient, more earth abundant. So the term which is used in energy materials, sustainability and all is that your material should be earth abundant. Gold is not very earth abundant. So we want to maybe substitute it with copper, which is more earth abundant, or titanium. We have a lot of titanium here, right? So it should be replaced with such material. Surface modifications in terms of decorating with nanoclusters or using defects or steps on the surface usually aid catalytic activity, or they completely make an inactive surface into an active surface. Experimental synthesis and measurement of these activities, of course, the final step. You cannot just do theory in vacuum and survive. Nobody will respect any system. But successful experimentalists are always on the lookout for theoretical modeling reports. Always. Because you need insights. From wherever it comes, it doesn't matter. So that's the message. Just going to my lab. This is computational material science lab. I think all the materials, the words got jumbled up. There's some display problems. That's why. Yeah. So this is an old photo. Back there behind me is Fasil, who is about to submit. Aparna is already a PhD. The person who is doing the Janus is the next in the middle. Anju, she is right now on leave. Adira is doing something. She is looking magnetic materials, and Amarnath is a BTech student who is now having his own company, and he helps us in our computational stuff. Present students are Fasil, Anju, Adira, Divya, and we have put out 5 PhDs from our lab, and we are supported by SCRT through a core research grant. This is the department where I work. Department of Physics was established in 2009, and we have 23 faculty members at present, covering all areas of physics. We have a PhD program. This is a little old slide. GATE, NET, JRF, and JEST. Now we also have a self-sponsored PhD program, which is open to all students. We have an MSc Physics 2-year program. We take admissions through JAM. And we have a BTech program in engineering physics. Okay. Thank you all for your attention. So, if you have any questions, I can clear them. Yeah. you can do the same kind of studies. In nanomaterials, you can do same kind of studies. There is a difference between this kind of codes which I use and just a nominal difference. Sets, as you said in Gaussian, code is used, which is localized functions. We have Professor Parmeshwaran in chemistry, who is ED student, and I sit in most of his doctoral committees, so I'm very familiar with the terms with the NPO analysis and all is very well known. You can use the same things for nanomaterials. In fact, you can build these clusters, and it's possible. And just like you build molecules, you can build clusters and you can use it. It might be, well, it might take a long time. Computationally, it might be much more involved in time than doing a molecule in Gaussian. But biomolecules, if you are handling, they're fairly big, right? Are you looking at some proteins or things like that?
No, sir. No, sir. Normally, synthesis first extraction ആണ് ചെയ്യുന്നതെങ്കിൽ അതിന്റെ LCMS analysis and HPLC analysis ചെയ്തിട്ട് high ആയിട്ട് അതിൽ നിൽക്കുന്ന compound ഏതാണെന്ന് analyze ചെയ്യും. Next, അതിന്റെ activity എങ്ങനെ increase ചെയ്യാം. Sometimes ഏതെങ്കിലും ഒരു additional ആയിട്ട് molecules എന്തെങ്കിലും add ചെയ്യുമ്പോൾ അതിന്റെ bioactive increase ആകാം. ഇങ്ങനത്തെ studies ഒക്കെ ഞാൻ ചെയ്യുന്നു.
ഏകദേശം ഇതുപോലെ തന്നെ, അതായത് we have an inactive material. I want to make one particular site active. So what do? I can substitute there or create a defect there or put something there like a cluster. So yeah, you can, just like you build your molecules, you can build clusters. That copper 5 cluster can be built, and you can just do a geometry optimization to it's actually exploring its potential energy surface. Analysis, the binding energy can be calculated, routinely calculate bond energies. Binding energy is like a bond energy. It's the adsorption bonding between the surface and the molecule. So you can just calculate it, E of A plus B minus E of A minus E of A. And it always give you the binding energy or the bonding energy, right? So all these things can be done for nanomaterials also. And you can maybe look at biomolecules which are used in synergy with nanomaterials, like metal nanoparticles. There are always these problems are like you inject metal nanoparticles as markers and all that for your fluorescence and things like that, right? Gold nanoclusters and all. So you can study such things. There are a couple of groups who are doing that kind of thing in NIT. I have done some, my student, this Fazil has done some calculation for gold nanoclusters. In that. It's possible. Yeah. Yeah.
Just said about the software.
About the software quantum expressor, like a free software for using DFT, quantum expressor. Okay. It's a quantum expressor as students can we calculate OER and HER everything?
Yeah, you can. You want to know whether quantum espresso, you can get it.
Yeah.
You can just download it today.
Okay. So we can also do the same things which you are doing in your presentation.
Absolutely. No problem at all. Quantum espresso is a code with a spirit of academics, I would say. Because all these are, the ones which I use are licensed. It requires funding. But quantum espresso is developed for academics. We stopped using that. When I started off in NIT Calcutta, I used to use quantum espresso. I didn't have any funding to buy VASP. But sometimes older versions of quantum espresso, we found that it's much slower. So there are potentials which represent the core atom, the core solar potentials. Those potentials apparently are better in VASP. That's why I went over to VASP. And now I have not used quantum espresso for the last 10 In fact, I don't know how really vast, I know how quantum espresso runs, but I don't know how vast runs because by the time I had 3 or 4 research students in my lab and they were handling everything. But the principle is exactly the same. Whatever I have done can be done in quantum espresso, maybe better also. Okay, and it has a very active forum. You can post your questions there. If you have a good enough computer, you can. There is a Windows version also. You can just download the binary and run. Or if you are more into computing, you can have a Linux machine. You download it there. You compile it yourself. You should do that because that's where you learn much more about the code, how to compile it and generate the executable yourself. Then you learn a little bit about how to maintain the code, all this. And then you just try out, so they have a test set of examples, you run it, and if it's working, it's fine, then you just move on. But the other thing that you should have is a visualizer. Because I have a crystal, I want to, I do some calculation, I move around atoms and see what's the structure later. Or I put a, I have a surface, I put an atom on that and it binds. I want to see how it looks in the end. Is the molecule stressed or not? So I need a visualizer. There are free visualizers. Vesta, P-E-S-T-A. Vesta is one such package. Okay. So visualize, and Vesta will only allow you to see things. It will not allow you to do things, I think. Because see, I want to start off from a crystal structure, bulk material. I want to clean, cut it. A particular plane. Like for example, I have an FCC lattice. I want to cut a 111 surface, HKL index surface, right? And then I take that surface and make 5 layers of that. That represents a 111 surface for me. In my code, I keep the first 2 surfaces to be moving, but the others to be fixed in their geometry. That means I am representing the bulk of the solid and the surface of any solid which is prone to moving around. Okay, so that's how I build. This called as a slab model. I show you a slab model, slab of code. When I do the calculation for that, the top layer of atoms will be going, but the bottom layers will be fixed to distances, which is the bulk gold distance. So we have to do these things. So to develop that model, I need a visualizer also. And some of this, this has now become a very big business because industry, petroleum industry, pharma industry, all these people require this. These packages of visualizers are very expensive. VASP comes with what is called as media VASP. And I just seen yesterday some license fee. It comes to 6 to 7 lakhs, and they have additional packages which come in. For example, if I want to know what's a transition state, they have something called as a transition state search. And that package is surprisingly an additional 7 lakhs. So easily you might spend up nearly 30-35 lakhs. I was doing this, I was asked this opinion by somebody in Calicut University, because Calicut University has got a very big fund, 100 crores or something, under the PM. This. So they've got a very big fund. And I said, if you have the money, you can certainly buy that. No harm in buying it. So, but you just search around for free visualizers. Vesta is one. There's something called XCRYS10, XCRYS10. That is another software. I think it allows you to cut surfaces. So once you can cut the surface, you can build any catalyst. A catalyst is essentially a slab, a surface. And you should know which is the most stable that will be available in the literature. Is the 111 or the 110 or whatever. Okay.
Thank you, sir.
Yeah.
Sir, this surface modification you mentioned, is it something that we only do on Catalyst, or is that possible now?
It can be done anywhere. See, surface modification, sometimes the modification is inherently there. Like I mentioned, zinc oxide. Zinc oxide has a lot of missing oxygens on the surface. And when there are missing oxygens, there are zinc atoms which have dangling bonds, unsatisfied bonds. Now, when that happens, that's equivalent to doping your system. Zinc oxide is a semiconductor, and these dangling bonds will come up either close to the edge of the valence band or to the edge of the conduction band. So you will see states coming there, and it will effectively reduce the banding. Okay.
If I may extend the question, in a previous lecture, they mentioned
lithium sulfur batteries.
Ah.
There's a lecture for this. And in that, they mentioned that a challenge they face is that sulfur has low conductivity. I was wondering if you could do this modification to somehow fix that.
Modification to?
In an earlier lecture, they mentioned lithium sulfur.
So that's fine. Sulfur has lot of conductivity. No conductivity. Okay. So, what's the system? Lithium. So, sulfur is attached to the lithium surface, is it?
They were mentioning it how in the electrolyte the conductivity by sulfur is reduced.
See, if you create defects, conductivity will always improve. Conductivity generally improves when, because there are additional charges generally. Okay. So, yeah, but then these defects can also sometimes act as traps. So both can happen. There might be improvement in conductivity. A defective solid is like a doped solid also. A doped solid is defective because you're spoiling the periodicity. Instead of some silicon, you're putting some phosphorus or something in there. So it certainly improves the conductivity, and that comes because of additional energy states which are created. But these can also result in some traps and other things which might lead to some localization of charges. It's also possible. Yeah. The lithium sulfur batteries are very important. Solid state batteries. Yeah. Okay. So, thank you.
I invite Dr. Bhatia to give a token of love. I invite Ms. Krishna to deliver the vote of thanks.
Good afternoon, everyone. On behalf of IPLC, PG Department of Physics and Home Science, St. Joseph's College for Women, Alabama, I would like to extend my heartfelt gratitude to all of you for being a part of this wonderful event today. First and foremost, I would like to express our sincere thanks to our resource person, Dr. Raghu Chattanaturi, for gracing us with your presence and delivering such an insightful lecture on computational atomistic modeling for the design of energy materials. Your words have been truly inspiring, and we are grateful for the time and wisdom you have shared with us today. And a special thanks to our organizing committee and volunteers whose dedication and hard work have made this event a success. Without your commitment, this event would not have been possible. Lastly, I would like to thank each and every one of you, our attendees. Your participation and enthusiasm have made this event all the more special, and we hope you leave with valuable takeaways. Once again, thank you to everyone for making today such a remarkable occasion. We look forward to your continued support in the future. Thank you and have a wonderful evening.
Dear students, now we have the tea break, and after that we will be having an online session. So please have your tea and snacks.